Hi. So thanks for coming to my talk and listening. I'm Andrew Warfield. I'm the CTO and co-founder at Coho Data. Coho is a storage company. We are based. We have offices in Sunnyvale as well as Vancouver, Canada. Our engineering base is out of Vancouver, which is where I'm down from. And so I'm gonna talk about a bunch of stuff that Coho does. Maybe just tell you a bit of the story of what we've been working on for the past 3 years. And I'm happy to take questions, although I've been encouraged not to take questions by these guys. So if you just have to yell and I'll repeat your question if you have questions, but I love them. I'm not going to use any slides. I'm just going to kind of tell you some of our experiences. So by way of background, I was a graduate student in the UK. I was one of the authors of the Zen hypervisor and was involved in the startup ZenSource that we did out of that. So I come from a virtualization background. I was involved heavily in the design of storage and networking on Zen, and have worked in storage for a long time. And I guess when we started Coho, when we decided to put the company together, we were looking at some ideas around scale-out software-based storage systems. And we prototyped up a system. The idea really being what I think a lot of people think about today when they think about software-defined storage, which is basically that you're going to take your storage stack as a piece of software, much the same way you take a hypervisor today. You're going to deploy that on a bunch of hardware that you own, and off you go, right? Storage is done. It was a really interesting thing because we spent a bunch of time building that around 2010, 2009. And we took it out and worked with a bunch of POC customers with the early stages of things. At the time, VMware ESX didn't use local disks for anything. It formatted them, but didn't actually take advantage of them because live migration obviously doesn't work and so on. Weirdly, the server vendors all make pretty good margins off of those spinning disks, so what you ended up with were loads and loads of servers that had VMFS formatted local disks that were doing nothing. And so the idea at that point was that we would just reclaim those disks and build an aggregating storage system. Right? Sounds like another product that you've seen recently. I said that there were kind of two weird lessons from it. The first one was that nobody wanted that thing, it turned out. Right? That we went and we worked with a whole bunch of customers, and nobody at the time wanted to take a software-based storage system and trust all their data to it. They wanted something that people had qualified against specific hardware that was going to work and that they could trust with enterprise data. And so that was a hard realization for us. The sort of corollary to it was that the people that did want it were so cheap that they wouldn't pay for it anyways, right? The super DIYers. But the other half of it was really where we kind of, I guess had our defining moment in some senses as a company. We took the system and we went and we started talking to a bunch of flash vendors. And at the time there was lots obviously of excitement around flash, and we went and talked to Fusion.io among others and started looking at the incorporation of PCIe flash into the system. So this was 2010. And really the first generation of PCIe attached flash. So flash that wasn't trying to look like a disk and was at least attached on a bus that was quite fast. And so we went out and we got a bunch of flash. We presented to Fusion. They lent us a couple of cards. And we found when we plugged it into the boxes that we had in our lab that we couldn't reproduce the numbers on that flash. We couldn't saturate it. And the reason we couldn't saturate it was because Linux was getting in the way, right? The flash was so fast that just Linux's block layer running against a raw device was unable to saturate or at least reproduce the numbers that Fusion was talking about on the hardware. So we did what all good systems people do, which was what we called BS, and said the card wasn't capable of doing this stuff, right? We sort of said, this is just a lie. It's marketing people generating the numbers, and we're done. And then we looked a bit more closely and realized that we had to get some of the software out of the way. And so we started to peel things away and optimize and so on. And once we did that first round of performance work with these initial Fusion cards, these 2010 I/O drives, the thing that we sort of walked away realizing was with a single flash device, we could saturate a 10 gig NIC. Right? We could deliver at 4K I/O enough data through the flash device to saturate the network. And this is a sort of like not very subtle thing, that once you do that, the value in building a storage system where you start adding additional flash devices, like we build storage systems in a lot of machines today, is very quickly diminishing, because you're not exposing any of the additional performance off of those additional very expensive cards. The extra bit of sort of interesting realization there was that when we did saturate the NIC, when we were driving the card very, very efficiently and focusing on its performance, the CPU was working incredibly hard in the system. It takes a lot of, controller I/O effectively to drive data across these two PCI devices. And so the insight basically is that, first of all, high performance flash, which is what we have from now on, needs to be a distributed system, right? It needs to be deployed on the network. Secondly, that it is so demanding and expensive as a resource that converging it with the same CPU that's hosting your applications is probably not a good investment of resources, right? Going to a fully converged model where you're having to scale out your CPU for VMs at the same rate that you're scaling out the CPU that's running your storage, it's probably not going to give you a good value on either. Finally, if you look at what flash is doing from an economic perspective, it is doing something that storage systems have not done ever, and certainly not in the lifetime of enterprise storage. It is falling in price by about 1/2 every 18 to 24 months. And so if you go and buy a great high-performance all-flash array today, in the model of that suiting your needs for 5 years, you're going to be really disappointed about 2.5 years from now, right? When that thing starts to come into useful utilization in terms of capacity, you will have been able to buy, for the same money, something that's 2 to 4 times as good. So this changes a lot of stuff for storage. And this is the premise for Coho, right? This is kind of the insights that we made on these systems. How do we take storage and make it scale out? How do we take advantage of the economics of flash as a commodity that's dramatically changing over time? And finally, with a lot of the things that we see happening in terms of appliance form factors, with hyperconvergence, both as appliance and as the EVO offering today, I would argue that it's not really technical merit that's driving a lot of those systems, right? It is straight up operational simplicity, right? That you want to buy a box that is storage and network and compute combined and not think about it anymore. You want this sort of, Google or Amazon or whatever the, picturesque data center, with poplar trees and birds flying around that is being painted for you. And I don't think that needs full convergence. Right, I think that, and we as a company are really from the perspective that there's a strong argument, especially in the face of the economics and performance realities of flash, that say that storage should be separate, right? It should be something that you purchase in the same way that you were trying to virtualize your CPUs 10 years ago to get good OpEx and price wins on the hardware. Today, this flash is becoming so precious and so capable as a performance-dense resource, you should be acquiring it and growing it, to need. And that demands scale out, right? So this is kind of a different take on scale out. It's an incredibly pragmatic one, right? It's not scale out because we can, and it's not scale out because you need to get to huge capacity. It's scale out because it makes an enormous amount of sense to buy what you need as you need it, and it makes an enormous amount of sense to have that system live much longer than your notion of a conventional array, right? That 5 years from now, maybe you've bought a couple of additional nodes over the course of ownership, and maybe you want to retire your original boxes. Right? And that shouldn't mean that you have to do a full-scale data migration right from one thing to another. So this is really borrowing a lot of ideas that we saw with Zen being deployed in cloud-style environments, right? Sort of utility-style model for storage. So that's the premise. Let me tell you a few interesting things about how we approached it, how we made it work. So we started from that sort of trio, right? That pair of things. Or the triple of things, that you had very fast flash device, you had a CPU behind it, and you had a 10 gig NIC initially, and this will go to 40 and to 100 as time goes on. That's our building block in the system. We are a software-based architecture, right? We don't actually build any custom hardware or anything like that. We go and acquire whatever hardware is at the appropriate point in the functionality and price curve. And so our first round hardware is a repackaged Supermicro. A lot of vendors maybe shy away from the hardware that they're using, and I'm completely unashamed about this. We're a software company selling on top of commodity gear. First gen product was a Supermicro Fat Twin, 2 servers, 4 10 gig ports, 4 CPUs, 4 PCIe flash devices, and a tier of spinning disks along the back, because you probably don't want to pay PCIe flash for all of your data, right? All of your data is not hot. And so we included a set of 12 drives across the back and built the system to auto-tier, right? The idea is that all of your I/O should be serviced off the flash, right? All of your writes should go through the flash. This isn't flash as a sort of cache on the read path, or flash as an afterthought. But over the time that your data lives in flash, you have an opportunity to identify the coldest data. And the coldest data should be progressively shuttled off to disk, right? So the disk fills in effectively as almost an archival tier for your least frequently used data. And so with that abstraction as the basis of scale, we needed to figure out how we could go and build a useful system. And this means that you have to decide on how you want to attach, right? So we decided, given that we had a lot of experience with virtualization, to start the company focusing on virtualized workloads. We went and looked at VMware. We looked at the attach points on VMware being Fibre Channel, iSCSI, and NFS, and the choice was totally obvious, right? That NFS immediately gives you a whole bunch of additional visibility into the VMs. It lets you do, prioritization on workloads. It lets you do all sorts of really great stuff. The problem is, though, that my NFS server needs to present a single IP address to my ESX hosts. And I'm building a scalable storage system. And the last thing I want to do is to put in a single gateway node at the head of it that is going to limit me down to a single NFS connection and make me look exactly like every other scale-out single master storage system in the world. And so this was a sort of like second fun technical insight for us. We went and started looking at what was available on software-defined network switches. We ended up looking at Arista's switch. At the time, theirs was kind of the most sophisticated offering and really had a lot of programmability. And so if you're not familiar with SDN, SDN is being touted as solving an awful lot of problems. And it solves, I think, some of them reasonably well. In particular, there's some really nice things to be said around the opportunity to provision and isolate traffic within a completely SDN-based switch network. The thing that's really interesting about SDN to us, though, is that these switches with OpenFlow or whatever other interface the switch ends up adopting allows you to program the chipset on the switch in a way that that chipset has been capable of for many years, but hasn't been exposed to applications. And so we were able to effectively abuse the switch, program the switch to treat traffic differently, specifically for storage, using OpenFlow. And so our product offering, again, is a hardware-based appliance. It includes an arbitrary number of these 2U 40 gig hybrid disk and flash nodes, and then a commensurate number of Arista switches, right? You can attach those as active-active. We use a 52-port 10 gig as a base. And the goal is to plumb full bisection throughput through between your ESX hosts and the data. One example of how we can do that is we can abuse the switch to orchestrate a bit of a lie for NFS. So when you configure up ESX to have an NFS-based data store, you give it an IP address. You give it, 10.1.1.1. That connection from your ESX host comes into the switch, but it does not map to a single host. Right? It doesn't terminate at a single point anymore because of our interaction with the switch. So what we can do is take that IP endpoint, right, the NFS server, and actually distribute it across all of the storage nodes in the system. Right? You can kind of think of this as all of those nodes are actually advertising the same IP address. But a subset of the aggregate traffic is going to each of them. And the TCP stack that's sitting there is effectively distributed across all those nodes. So if you end up with 2 connections coming in that are saturating a NIC, the system can look at the throughput being pulled off the system, and it can move one of those connections over. We can dynamically move requests both to balance resources on the network and to move traffic closer to the data that it's accessing. So this has been a really interesting bit of the system. The switch actually lets us do a lot more, right? The really cool bit of OpenFlow and this programmability on the switch means that we can build an isolated L2, right? An isolated Ethernet for our interconnection traffic between these nodes, and we can do whatever the heck we want on there, right? We don't have to use any conventional protocol. We can abuse forwarding tables on the switch to do interesting things in terms of how packets go to data and so on and so forth. There's a lot of really, really fun stuff to be had in there. So I guess that's that end of things. How am I doing for time? So I kind of talked about, yeah.
I do have a question for you if you want to get into it.
Sure.
So how is data stored and also how do you recover data, or like what are the other features related to the resources that you're maintaining?
Okay. Yeah, so the question is, how is data stored? What resources are associated with data, and how do we sort of represent consistency and so on and so forth? So again, I come from a server virtualization background, right? And one of the really core tenets that we spent a lot of time thinking about when we built Zen was that the simplest conceivable system at the base, at the hardware level, was the only way to get really, really strong performance and security isolation across all of the things that ran on the system. That as soon as you started exposing shared interfaces down there, as soon as you had a resource, whether it was a CPU that you're scheduling between or a bunch of memory that you're paging, that you introduced these complicated edges that became very, very difficult to reason about and to get to perform predictably under load. And so as we've approached this system, my sense is that this PCIe flash behaves much the same way, right? And it's like, as a really, really quick digression, it's like worth thinking about how fast this flash is getting faster. But these devices are astoundingly fast today, and over the next 2 to 3 years, you will, without blowing things out of proportion, I don't need to exaggerate, you'll see 2 and 3U boxes that are capable of tens of millions of IOPS, right, out of flash. It's just, you know, parallelization at work, basically, on these platforms. And so the last thing I want to do is to presume what storage interface you want on that and build a whole bunch of shared resources down at that base. And so the way that we built the stack was basically to virtualize at that layer, right? So the flash to CPU to network lowest level of the stack is actually only virtualizing the address space, right? In fact, if PCIe namespaces, NVMe namespaces did a bit better job of what they do now, that would be sufficient to do what we are trying to do down there, right? What I want to do is take the flash device and make it addressable as a point on the network as a sparse address space. And I want to present up arbitrarily many of those, and I want to be as little in the way of that performance as I can. On top of that, using those same nodes, although you don't necessarily have to build the system that way, we built a hosting layer for your protocol implementations. And so you have this API that lets you address, you know, isolated chunks of flash on the network, right? You can talk to these named flash devices, but only to your data on them. You can take that and in a library, which we, you know, build and incorporate in our NFS implementation, implement things like striping, replication, right, failure recovery and stuff like that, but it's pushed up the stack. And so the idea there is that our initial product, right, the thing that we sell today is a scalable NFS v3 server, right? It does a whole bunch of stuff that NFS v3 wouldn't traditionally do in terms of getting much broader bandwidth off of the ports because of spreading that IP address out. But under the covers, there's nothing preventing me from taking and implementing a completely different protocol attach, right? Taking an application and having it talk directly to the network attached flash and deploying that in an isolated manner alongside the NFS implementation, which is really the sort of direction that we, you know, anticipate things going, right? That a lot of these storage protocols are 20 and 30 years old, and they're driven by disks, right? They're driven by a notion of storage, which is a closet that you send some person to go in, and they're, you know, probably pretty drunk, and some point they come back and they have your data, right? That I/O is such a terminally slow thing that you can't screw it up. And flash is the opposite of that from now on. And so any sensible storage system design needs to both allow you to work with the workloads you have today, right? Because you can't sell the brave new world in the time frame that a startup has runway. But you also need to, you know, anticipate how you're going to change and get people off of that. And that's really what the system's kind of designed in anticipation of. Does that answer the question you asked? Okay, so I've got a few more minutes. Let me maybe talk about one other aspect that I think is really interesting about the design. So the company comes obviously from a pretty broad technical background. We do lots of like really interesting stuff, and one of the realizations that we made that kind of falls from both Flash and the sort of mix, the change in mix of resources that you have in the system, is PCIe Flash as a commodity today, as a device, even if you like do a really good job of negotiating on the cost of goods from the Flash vendor, is in the neighborhood of $2 a gig, right? Raw, unreplicated, uncoded Flash. It's a very expensive piece of hardware, and that's going to fall. It's that version of Flash is not going to get cheaper than disks anytime soon, but it performs very well. We'll see a stratification of Flash where you start to see kind of Flash that's more intended for capacity than for performance or things like that, right? Certainly starting to come. And the thing that we kind of took from all this was that your storage environment is not going to get any simpler over the next few years in terms of the media that it's composed of, right? You will have very fast Flash at the top. In fact, you may have, DIMM attached non-volatile DRAMs right at the very top. As you go out the bottom, you're going to have spinning disks or capacity Flash that reads really well but doesn't write very well, or things like that. And so the storage system needs to figure out this tiering. And this tiering is something that storage people have messed around with trying to get right for a long time. We've had things like HSM and all sorts of tape tiering things and so on in the past. Weirdly, these systems haven't dealt with either media that's as fast as Flash and disk is a slow tier. They also haven't dealt with the amount of compute that's able to do analytics on tiering itself. One thing that you would never do with a spinning disk-based array is take a complete I/O trace of every request that you pump through the system and then read it back to make decisions. Right, you don't have the I/O budget to store that trace, and adding the seeks to go and fetch it while you're doing production workload would be asinine. But with Flash, it's a very, very plausible thing to take a complete I/O trace and pump it into a buffer in Flash and gradually trickle it out into free space on disk. That's a sensible thing to do. While it's in Flash, you can do a bunch of analysis. And so we hired a team. I have lots of ties into systems and academic research, and so we have this really fun team of guys that are a mix. One of them is a storage guy that I've worked with for a long time, who's absolutely brilliant at building systems. Another guy is information visualization and stats guy, right? That worked for a hedge fund for many years doing high-frequency time series analysis for trades. Right? It actually looks a lot like storage tiering if you twist your head in a certain way. And then on algorithms, so these guys. Basically have taken over the past few years and done a whole bunch of analysis on this tiering problem and understanding actually the workload characteristics of things. And so if you come by our booth, we have a demo of the first version of this. And one of the things that we're able to do is under a live workload, we can very accurately model what's called the working set of that workload. Right? We can look at the data that is being accessed over time. We can tell how much of it has been accessed, piecewise over progressively longer periods of time. We can tell you how you would have done if you had more or less Flash. And so this thing ends up being really, really interesting. First of all, from a performance diagnostic perspective, if you have a system that is behaving poorly, right, against conventional storage hardware, that ends up being a really, really painful why question. Right? And the answer is usually throw more hardware at it, and maybe it will get better. Right? Usually that involves calling in the performance guy from the company, and he comes in and does a bunch of stuff at the CLI and goes, no, more RAM and probably some more controllers is good. The thing that I can show you in the system is basically for a given workload, I can show you a graph where you run it for a period of time, and I can show you how it's going to do in terms of hitting the various types of memory it has available given that amount of memory, right? How well it will do as you scale up performance. And this ends up being useful in two ways. First of all, it's a great performance diagnostic tool, right? It lets you understand that some of your workloads are actually really, really expensive and damaging to run, right? That there are workloads that have huge working sets that for you to satisfy in a traditional LRU are actually going to hurt all of your other workloads very badly. And it lets you make that operational decision, because that's not a decision the storage system can make. The storage system doesn't know that this is actually important. And so having this sort of visualization is super useful. Secondly, looking for the elbows in these curves ends up being an incredibly useful way to assign resources to the various workloads. And so that's effectively where the system's going in terms of carving up the flash that's available, and not only providing hard guarantees in the forms of QoS, but doing a really good job with Slack resources at assigning them in the way that's going to get the biggest win for each workload. And so that's kind of, we call that Cascade. I didn't come up with that, but it's not a terrible name. And it's pretty neat. There's a research paper that we've actually written on it that'll be published in a few weeks. So it's actually like there's computer science going on in the system. Anyways, I think that's largely it. I could keep talking for a lot longer, but I will not. I'll thank you all for coming. Our booth is, kind of, I think it's 835, but I might be wrong. It's backish, left of middle, near the very tall Micron booth. We, just to reiterate, sell a converged storage networking system that is really, really cool. So thanks for your time.